Welcome to this next lecture on acoustics. Today I would like to derive the solution to a simple system that we call a pulsating sphere. It is a very standard problem in basic acoustics. So what this is there is a sphere of some nominal radius a, and on top of it the sphere now oscillates with a velocity. Okay. So, the surface velocity moves uniformly as u at a comma t is some u0 e to the power of j omega t. Okay. So, this sphere uniformly increases in its radius and decreases in, so it is called a pulsating sphere. Okay. It is a very standard problem in acoustics, and it is a one of the simple models for a speaker, for an acoustic speaker. Okay. Now, this is a spherically symmetric object. It is a spherically symmetric system. And therefore, we can assume the pressure. So, we are looking at external radiation. Okay. We are looking at radiation exterior to the sphere. So, we can take the solution to be of this form: a tilde e to the power minus I k r by 4 pi r plus b tilde e to the power of I k r by 4 pi r, and this is harmonic. So, it is e to the power j omega t. Okay. So, now, so we have to find the a and b constants, and the boundary condition is the velocity at the surface, that means r equal to a is u0 e to the power of j omega t. Okay. Now, this is a system where only outgoing waves will survive. Okay. Outgoing waves only, and so B represents incoming waves. B represents incoming waves because of its sign. Okay. It has e to the power of j omega t plus j k r, and so these are incoming waves from r equal to infinity. And since the source exists only at r equal to 0, centered on r equal to 0, we have a sphere pulsating centered on r equal to 0. So, waves will go only outward to infinity, nothing will come back from infinity, and therefore B tilde is 0. B tilde we set to 0. Okay. So, then my P tilde r comma t is given by only A tilde e to the power of minus j k r by 4 pi r e to the power j omega t now. We have to use the Euler equation, which is always our friend when it comes to relating pressure and velocity. Pressure, let me use V, velocity V, or let me use U tilde, pressure and velocity. Okay. So now that we have spherical symmetry, the Euler equation is del P tilde by del R is equal to minus rho 0 del U tilde by del T. Everything is now solely a function of the radius. There is theta phi symmetry. Okay. So now if we do this operation, what do I get? I get A tilde, I will leave out the time dependence, okay. A tilde by 4 pi minus j k e to the power of minus j k r over r minus 1 over r square e to the power of minus j k r. This is del p del r, okay, and that is equal to minus rho 0. This particle velocity has the same time dependence j omega t. So, I will bring in a j omega and u tilde of r. Okay. So, I am taking shortcuts. By now you should get used to it, because carrying this j omega t all the time is very cumbersome. Okay. So, now what do we have here? We have let us see, A tilde by 4 pi e to the power of minus j k r over r let us see what we are going to do. Okay, over r is equal to minus j k minus 1 over r is equal to minus j omega rho 0 u tilde of r, and this minus can be removed. Okay. So, what we have now is so let us combine this. We get 1 plus j k r over r, 1 extra. Okay. This is this term. So, what we have now is A tilde by 4 pi r square e to the power of minus j k r into 1 plus j k r is equal to j omega rho 0 u tilde r. Okay. So, let me carry this to the next page. So, now the main idea is I want to figure out A tilde. Okay. So, how do you figure that out? The condition at r equal to a is that my u tilde of r is this value u0. So, if I set r equal to a, what I get is a tilde e to the power of minus j k a by 4 pi a square 1 plus j k a is equal to j omega rho 0 u 0, and therefore a tilde is equal to j omega rho 0 4 pi a square u 0 into e to the power of j k a by 1 plus I k a. Okay. Now, we will define the source volume velocity, source volume velocity as volume velocity q is surface area into the velocity. This is the volume velocity, the volume that the pulsating sphere puts out puts out in per unit time. This is the volume, so volume velocity. So, now a tilde becomes j omega rho 0 q e to the power of j k a by 1 plus I k a. So, I have figured out this unknown. This unknown is now figured out. So, I will know the pressure. Okay. So, what is the pressure now? The pressure at r function of time is equal to j omega rho 0 into q by 4 pi r e to the power minus j k into r minus a over 1 plus j k a. Okay, this is the pressure, pulsating sphere. Okay. So, one thing to notice is that there is this j omega rho 0 in it, there is this volume velocity q in it, there is a dependence of 1 over r in it, okay, and there is this factor 1 over 1 plus j k a in it. So, these are some typical terms that will exist in pressure fields. Okay. So, now just so that we get some insight, if Ka is made very small, okay, so Ka is called the Helmholtz number. Ka is the Helmholtz number. And if Ka becomes small, okay, then what we can say here is that K is twice pi by lambda and we have A over here. So, that means A over lambda is becoming very small. Okay. So, either A is becoming small or lambda is becoming big. Okay. So this approximation or this assumption leads to what we call a monopole. A very small source, a point source, leads to a monopole approximation. Okay, small source relative to a wavelength. Okay, all relative to a wavelength, to relative a wavelength. Okay, else what is small or what is big, it doesn't make any sense. Okay, if you find something big, that can be bigger. If you find something small, can be smaller. So what is the real way to do it? It's the dimension of the source in relation to the wavelength it's radiating. If that is small, much smaller than 1, then we call it a monopole approximation. Okay. So now if we go to a monopole approximation, P tilde monopole is given by j omega rho 0. We will keep the same source strength by 4 pi r e to the power of minus j k r. Okay. So you can kind of see that it looks like the green function. Okay, this looks like the green function, or the what I mean is the free space green function. This looks like the free space green function. Okay. Now from here, this is our main term. This is our main term. Okay. So what is the let's see one more. Okay, let me use this expression. Copy. Paste. Okay. So from this equation, if I substitute my A, if I substitute this value of A, which is j omega rho 0 q e to the power of j k a by 1 plus j k a. Please notice that I use I and j interchangeably. I am not very particular. Both, okay, implies the imaginary number. Okay. So into j k by r plus 1 by r square e to the power of minus j k r. I will take out the sign, j omega rho 0 u tilde r. So now let us see, j omega rho 0 goes away. Okay. And yeah, so let me again, I will have to copy this. Okay, so I don't need the top, I don't miss this one, and let me raise this a little. Okay, so now my u tilde, the particle velocity at a certain radius, is now given by q by 1 plus j k a e to the power of minus j k r minus a and 1 plus j k r divided by r square. Let me just check. Okay, there is A and there is a 4 pi, sorry. So there is a 4 pi. So there is a 4 pi. Okay, so and I can put the time e to the power j omega t. Okay, now here also if Ka is very small, Ka is much smaller than 1, okay, then the particle velocity u tilde r comma t, let us say, becomes equal to q by 4 pi r square 1 plus j k r e to the power of minus j k r into e to the power j omega t. Okay. Now, so this is the velocity, particle velocity, acoustic particle velocity, acoustic particle velocity from a monopole, okay. And let me just write down the pressure that we may have forgotten. P tilde r comma t from a monopole is j omega rho 0 q by 4 pi r e to the power minus j k r. Okay. So now we have here one term, everything remaining same, we have a term here which is 1 plus j k r by r square. I will divide by c and multiply by c, and this omega by c I will take as k. So I get j rho 0 c k q by 4 pi r e to the power of minus j k r. Yes, so there are some parallels. Okay, so here I have, so particle velocity, I have two terms, 1 over r square plus j k over r. Pressure, I have j k over r. That is my focus. Okay, the radial behavior is my focus. There are other constants, which are not at this point important. Okay, so now if my radius goes to larger and larger values, okay, then u of r comma t is dominantly jk by r, okay, and p tilde r comma t is also dominantly jk by r. There is no other term over here, okay, and therefore when we move far away, the field is called far field, the sound field is called far field. Okay, far away from the source. Again, there are non-dimensional numbers. So, we will typically say k times r is much greater than 1. We do what is far and what is near is not very clear just by distance. So, we again have a k times r or r over lambda, okay. But here let us just say that we go far away from the source r, okay. Then particle velocity is dominantly jk by r, pressure is jk by r. So, in the far field of the monopole, the particle velocity is in phase with pressure. Okay, so this is important information. This information or this understanding is important. When particle velocity, this is dominantly, okay, because there is the other term still there, I just ignored it, neglected it, okay. So, this is dominantly. When U is in phase with pressure, then power is carried efficiently, and then power is carried efficiently. Power is carried efficiently. Okay. Now, the other side is when r goes to smaller and smaller values, because we have monopole there, r goes towards 0. So, what happens is that we have u tilde of r comma t given by 1 over r square plus j k by r, and so in this, as r tends towards 0, this term becomes to dominate, okay. Then u tilde of r comma t is dominantly 1 over r square. So, what if, and that region is called what? We call it the near field, okay. And near field also is denoted through a non-dimensional number, typically kr much less than 1. I am not doing it in this case, but kr much less than 1. So, in the near field of a monopole, particle velocity is proportional to 1 over r square, and pressure is of course proportional to j over r, okay, j over r. So, they are 90 degrees out of phase. So, particle velocity and pressure are 90 degrees out of phase. Okay. When that happens, power is not efficiently carried, power is not transmitted efficiently. Okay. So, now let me just go with the main main expressions over here, the power or intensity, what we call, so we have particle velocity over here, and pressure over here. Okay, let me see pressure. If I take the ratio, of pressure to particle velocity, we add the e to the power j omega t. Okay. So, these are general expressions, not for a monopole or anything, general expressions. Okay. So, if I take the ratio of pressure to particle velocity, you know this is the acoustic impedance. Okay, we call it Z tilde acoustic. Okay, this is another impedance. Okay, we have seen before the mechanical impedance. Okay, so now from this acoustic impedance, we are going to find implications of being in the far field versus being in the near field. This we will do in the next class. Okay, I will close the lecture here. Thank you.